Hey guys, this video is going to be the part one in the two-part series of From Geometric to Physical Optics. And the main question or objective of these two videos is going to be, why does the light change direction or bend when it enters the new medium? This was the question we came up with. We've spent now almost 2 weeks going through geometric optics, and what we've discovered together is that when light passes through a substance, it bends, right? And we've used a ray model of the light, just basically using straight lines to represent parts of light. We've isolated down the infinite amounts of light into just these straight lines so that we can describe the phenomenon. And that's the key word. We've just been describing what's happening, right? Just like kinematics just described what is happening with motion, but not necessarily why it's happening. So that's what we're trying to do in this part one. And part two is describe why is the light bending. A new term to look out for in this video particularly is diffraction, and in the next video there will be a different one. Just trying to alert you to it as it comes up. So let's just quickly state what we know already, what we know about when light hits the surface. So I'm going to just quickly draw here a boundary between two surfaces. Let's say that this is less dense and this side is more dense. Okay, we draw our normal line in always because that's our reference to describe the light changes. We have an incident ray hits this surface right here, and it bends. As it goes into more dense, this angle between the normal line gets smaller. Now we know what happens between these 2 points, right? We've already started to describe even more of the physical changes. We've said that the speed will change. So the speed in this case will decrease, right? And this is all just review, so hopefully you can fill in more details. We know that the wavelength, lambda, also decreases. And the reason that we can say that must happen is we know that the frequency is source dependent, and we know that it can't change as far as we know right now. Okay, so frequency is source dependent and therefore constant. All right. We also know that the angle changes, right? The angle gets smaller. All right, so these are all just points that we've sort of come up with. We also saw that when the wavelength is different, the index of refraction is different. There's an inverse relationship. A longer wavelength has a smaller index of refraction. And this we use to describe why light disperses, right? And that each wavelength of light that makes up the full band of light, right? That's a band of wavelengths all grouped together. They all change speed and therefore all have different angles of refraction because they experience different indices of refraction, and thus the light disperses into its colors. So now we're trying to describe why this happens. Okay, so that's what we don't know. This over here on the right is what we do know. So a proposed way to answer this question is to combine the ray model, which is on the left there where we just measured angles right here and right here with straight lines, combine that ray model with the wave model, which kind of goes through these things over here on the right. We want to try to marry those two together. Because the wave model offers more detail, but the ray model offers structure, right? A skeleton almost that we can put the details on. So we're going to try to marry the two and see if more questions arise. So let's skip to a new slide so we have some space here and try to investigate how can we put these two things together that might start to answer the question of why does this happen. Alright, so we don't know the whole story. And if we're trying to marry the wave model and the ray model that we have so far, we need to know more. And so we're going to turn to Francesco Grimaldi, S.J. Yes, he was a Jesuit priest who lived in the 1600s. I think he had died by 1695 or 6, somewhere around there. And he is credited with the discovery of diffraction. And his main sort of idea is summarized there in the text on the right-hand side, which says light propagates and spreads not only directly through refraction and reflection, but also by a fourth mode, diffraction. Now, you may be thinking, well, where's number 3? We haven't got to that yet, and so we will talk about that soon. It's really important that we understand this new term diffraction, so I'm just going to quickly describe to you his experiment, which was the following. In a dark room, he let a thin amount of light, or a very small cone of light, into the room. So imagine this space over here on the right as being a chamber, a dark room. And he lets a very small pencil of light into the room. Maybe there's a little opening right here. All right. And in this, maybe let's make this the light beam. All right. In this cone of light, he places a pencil or a rod or something. So we're looking at it from above, so I'm just going to draw a little circle. Oh, wow. Wrong tool. I'm going to draw a little circle here to represent the top of the rod. Okay. I think I better use a different color. So we're looking at it from above. And what he noticed was if this light was sort of shown onto a white surface, so like a white screen, that you would obviously expect to see a shadow. So here's the white screen that the light's hitting. Now what you'd expect is to see a shadow of the cone, or the shadow of the rod somewhere over here on the wall. And you'd expected, he had already sort of described shadows and shown that shadows are slightly wider, geometrically geometrically wider than the object sometimes, and that was very, sort of cleverly put geometrically, he described. But what he noticed here when you do this is that the shadow is actually wider than you would expect geometrically, and on the fringes of the shadow, so on the very edges, you would notice there was some color. There was red on the outsides, then there was this sort of like sometimes green in sort of next to the red, and then there was even blue closer to the object. So you could see these sort of little rainbow effects on the edges of the shadow. And what he concluded is that when light hits the object, it's bending or spreading or moving in a different direction than it did before. Right? And this is not because of refraction, because the light's not passing through the pencil or the rod or whatever you place there. The light is bending around it. And somehow the bending around it caused this sort of color revealing that we've seen through refraction. But it's not through the same mechanism. Right? And so this idea, diffraction, was actually what inspired Isaac Newton to write part of his optics that we talked about before. And so it's kind of cool that a Jesuit scientist is sort of credited with the most important idea in light that really spurred a lot more discussion. So now that we have this idea of diffraction, and we can define it as the light sort of bending around an object, okay, it was then further described by a guy named Christian Huygens. He's a Dutch physicist, kind of overlapping in time, and so let's take a look at that and see what else he found. All right, so now we're looking at Christian Huygens here, Dutch physicist, the cool hair over there on the side, and he then developed this idea that not only is the light bending around some object that's in its path, but additionally, the light is passing through a gap, or it can bend through a gap. And here we have two models overlap. We have the wave model, and then we have the ray model. Now, it's important for us to distinguish one thing. The dark spots, maybe these dark bands over here, we're looking at the wave from above. Those are perhaps the troughs of the wave, and then the crests are the white bands that are in between. So you can imagine kind of like waves like this. We're looking at, I've kind of tilted the wave sideways so we can see it that way, and try to imagine that as you look at this image. All right, so let's get rid of that. What he saw was that when light shines on a car that has a little kind of cut in it or a little hole in it, the light sort of propagates out spherically like you see on the other side. So what he's basically doing is he's showing here that light can be isolated as a little point, right? So if we were in the room on the right here, we would just see this as a little point source of light, right? Whereas if you were in the room over here, we've got this whole big band of light that's hitting the wall. And so now what we're going to try to do is explain why the red arrows look the way that they do as the light passes through this little opening. And remember, the whole point here is we're trying to explain why the light changes direction. Okay, so let's try to take a look at that. So Mr. Huygens uses this little image that I've just shrunken down to explain that light at every point on the front of the wave behaves as or can be explained to behave as its own, as a whole bunch of little point sources of light. So the wave front, which is the front of the wave, okay, hence the term, would be the front part over here. So it would be all of this. So that's when we're describing the wavefront, we're talking about that whole region over there. And what he basically says is that if this little region right here, this little piece right here behaves as a point source of light, then why not this little piece right here, or this little piece right here, or this little piece right here? Couldn't they all behave as little sort of wave fronts of light? And he finds a geometric way to explain that that is possible. So I'm going to pull up another picture here to show you what I mean and how he used that idea. All right, so here's a wave, right, that we're looking at from above, and the source is somewhere over here, and it's shining this light outwards, and we're looking at the wave crests and troughs from above. So try to imagine this as like a piece of rippled paper or water waves all going like this, and what regions we can describe is this point right here all along the front of the wave can be known as the wave front. Okay, so when we refer to that in questions or when you read about it, that's what they're looking at. Now what we want to do, as we always want to do in physics, is predict things. So we want to predict where will the wave front be in t seconds, right? Well, if you kind of look back as where it's been to help describe where it will be, you can say, well, at one point in time the wave front was right here, and another point in time the wave front was right here, and if it continues this pattern, at some point in time, well, the wavefront's just going to be here, and it's going to look exactly the same. And he says, well, wait. If in the small picture up there, the top next to his picture, if we are considering light as a little point source instead of this line source that we have here, or bunch of point sources, then how does each little point source of light make up this sort of whole band of light that's all combined? And so what he proposes geometrically is to do the following. All right, so let me try to erase some of these lines. Oh, well, I guess it won't let me. So let's just take a point, pick any point on the wavefront. So I'm going to pick this point right here. I'm going to call that point A. And what I'm going to say is that at time t, that point of light could be here, it could be here, it could be here, it could be here. I mean, it could be in any of these places, just that one point. Basically, it can be anywhere along this arc, is what he says. All right, so let's pick a different point. Let's pick point B over here. And the same thing is true. At any time t, that point of light could be anywhere along this crest. And so what he says is if you keep picking points of light, what you see is that a line that's tangent to all of those arcs is the wavefront. So each of those little possible locations of the light at some future time all add up to this new wavefront. And yes, it predicts where the wave is at some later time, somewhere along this band, which is makes a lot of sense, I think, if you think of the pattern of where it's been, which in science is what we're usually trying to do, right? So if I zoom into this picture again and I take a look at that, if I eliminate all the other points or a lot of the other points, I end up getting just this sort of rounded possibility of the light being at all these different places. And that is true, right? And that's kind of what you would see happen. Now, this is interesting because if you look at the ray model, the red arrows, you can see that the light has appeared to bend as it passed through the little hole, just like we would have drawn the arrows of light that were hitting a surface and refracting. Now, are they doing the same sort of pattern as refraction? No, but they are bending, and that's what we're trying to show here, is that through this idea of diffraction, perhaps diffraction will actually explain how refraction is happening. So if this was a little bit confusing, this slide for you, watch it again and try to slowly break it down and explain and try to reason through what I've just shown. Now remember, we're trying to explain why the light changes direction when it hits a different, more dense surface. So that's what we're going to do next and take a look at how this is maybe possible. Alright, so it helps to look at reflection first because it's a little simpler, and then we'll look at the refraction. So if we imagine this plane of light, this planar light, approaching a surface, this reflecting surface, which is denoted by the line x prime, we pick 2 points, point A and point B, on either end of the front of the wave. And you can see there the ray, the red arrow, is always 90 degrees, right, to the surface of the wavefront. So that's something to note. Now what we want to do is we want to predict where point A will be at time t when point B strikes the surface, right? So the distance that point B travels will be this, right? So at some future time, point B is going to be there. Where will point A be? Now we know that point A, this little sort of point source of light on the front of the wave, is going to reflect off the surface. Now, its ray length needs to be the same as B, right, in the same amount of time. And so we draw that line and we say it can be anywhere along some arc, right, in any of those possible places along this arc that forms. Okay? And so here has a very nice picture that's sort of better drawn that I'll show you here. Let me just erase that line. Okay. So you can see here, when point B reaches that point C, right, that length has to be the same as the A hitting that arc. And if we draw a line tangent to the arc to point C, because that's where where point B will be at that time, right, we see this nice wavefront forming over here, which is kind of cool because it shows very nicely then kind of how the light is going to bounce off, right? It's going to bounce off like this. And if we drew a normal line to both wherever this point is and wherever the ray for the other set of waves is, you can easily see, I think, that this normal line over here shares the same angle on either side from the incident ray over here and to the reflected ray over there. All right, so that arc, that little wave point that we took, point A, where it forms, there's a whole infinite number of little points along here, and they will each form in the corresponding space over here on the other side. And it shows that the angle of reflection is or will be the angle of incidence. Now let's take a look at it with refraction. So to review this again, if that was a little bit confusing for you, look at it slowly again and then move on to the refraction. Okay, now for the same idea with refraction, we have once again that boundary x prime where it's going to be going into, let's say, a more dense medium. And once again, we're trying to use prediction, right? So we're going to say point A and point B, we want to predict by the time point B strikes the surface, it will have traveled this distance, right? And we're going to represent that distance with v1, so speed times time, which would give me distance, right? Now we have observed that A, in the same amount of time, t, won't have traveled so far because it's moving in this new substance, which is slower, right? So it's going to be moving at the speed v2 times t to accomplish some displacement, right? And it can be anywhere along this path, right? Because all those radii are equal length, and we'll see there that that arc, right, if we drew the line, if we're following the pattern we've had before, if we draw a line that's tangent to the arc, right, we can see that we're starting to change directions. Now, because of my poor drawing, that's maybe a little bit confusing to see, so I'm going to pull up this picture that I've used, and I will quote my source at the end. So right here we have point A. You can see there where the new wavefront will form because of point A, right? And it is not going to be parallel to this wavefront. So you can see that the light's bending here, right? And it's forming this sort of new direction where the wavefronts will be in that direction. So I'm going to pull up another picture here for you to look at that maybe makes it a little bit clearer. And there we have it, right? And you can see there kind of the progression of how this all happened, right? And I think it makes a lot of sense, or at least it's a way to reason what's happening, right? You can reason a lot of what's happening. So let's just try to summarize all of this really quickly, and then hopefully it will kind of start to answer the question. Alright, so in conclusion, hopefully you can answer the very main objective. The question we started this whole long video with was, why is the light changing direction, or why is the light bending? And what hopefully you see here is that we were asking basically, why is the light refracting? And we've said that it's refracting because it's diffracting, right? So we've really just sidestepped the question, or at least made it more complicated. So diffraction, the bending of light around something or through an opening, is causing the refracting or the refraction to happen. Now, hopefully this has raised a lot more questions for you. If the light is diffracting, okay, I can buy the explanation. If the light is diffracting, what is it diffracting around or through? Because it's hitting this big blob of surface, right? And so if we go to our particle idea of matter, the microscopic view, you hopefully can start to propose some hypotheses of why or what the light is diffracting around or through. And I'm going to leave you with that. We're not going to describe it anymore, but I am going to ask that you complete the post-video questions to make sure that, one, you understand, and two, to propose some new questions that you can maybe start to use your reasoning to answer. So I hope the video, at least in some way, helps you sort of marry the ideas of the ray and the wave model of light even a little bit more, and at least offer some, a broadening of the picture of how the light is behaving as it changes from one medium to the next.